Okay, so let's get started. Last time, if you still recall, we played the Gaussian graphical models a little bit, right? We basically are kind of telling an elaborate story from what we thought to be a multivariate Gaussian distribution. First of all, we call it a Gaussian graphical model, and then we basically found that the inverse of the covariance matrix leads to a Markov network, and that could be used for structured learning. And then there are some algorithms that we developed called neighborhood selection, which is a reflectance of the property of conditional distributions inside a Gaussian graphic model, right? The conditional distribution of a node given all the other nodes in a multivariate Gaussian is a linear regression, right? And then you can use other tricks to derive some graph property. So today we are going to explore some other properties of the Gaussian distribution. Again, in the context of a bigger graphical model story. And today we're going to talk about sequential models. So we've seen a few sequential, well, let's begin maybe from a non-sequential model first. I think people are now familiar with the first two models already, right? The mixture model is a model where you have the observation x, and then you have some hidden variable y, which indicates the source of that observation x. You can imagine the x to be a discrete random variable such as word frequency, or it could be a continuous random variable such as temperatures and other measures. And then what does this y indicates? What does y mean here in a discrete sense? In the mixture model sense? Which mixture come from, right? Which conditional distribution come from? Okay, so basically here, P of x given y is a conditional distribution of the observation, and y is a indicator. You can basically, extrapolate that hidden variable and turn it into continuous y. Okay, so graphical model-wise, it's giving you the same graphic model, but it gives you a different type of model called a factor analysis. So in here, y is continuous. Therefore, it is not having the meaning of a indicator function or mixture component function and things like that. But we'll see actually what it translates to. It has some other meanings. And it's a very interesting model that you want to learn so that you can understand now why these days people are talking about embeddings and talking about deep network features. They all have some relevance to these type of models. And then I guess we know the beauty of graphic model is that you can take the smaller graphs as building blocks to build bigger ones. And I hope you already realize that a sequence of mixture models, whether it's a discrete mixture model or continuous mixture model, they can be turned into a HMM, right? You basically just tie together all the mixture models into a time sequence and let the label to evolve over time, and that's a hidden Markov model, right? And we learned hidden Markov model not only from here, but also from 701 and other machine classes. So I intentionally skipped the derivation of its inference algorithm. I use that as a running case in many cases to talk about the message passing, to talk about variable elimination, but I didn't talk specifically about the inference algorithms in HMM. Do you remember what algorithm people use to do the inference in HMM? I heard of Viterbi. Yes, that's one of the algorithm For doing what? Yes. You can do the inference on one hidden state. You can do inference on all the hidden states. You can also infer what is the distribution of the hidden states. You can also infer what is the most probable sequence of hidden states and all these. Each one has a different algorithm. Can you name a few, give me a few names of those algorithms? This is a review, okay, just to check whether you still remember something from earlier classes or even earlier lectures from this class. You know what okay, I heard you saying forward and backward algorithm. You have anything to add?
I was going to say Baum-Welsh.
Baum-Welsh algorithm, okay, great. Okay, wonderful. That's a very, very good preparation. What I'm going to do today is to, again, make the same extrapolation from here to here and also here to here, so that you also could have a continuous hidden states. And all the algorithms that you mentioned, Baum-Welsh, forward and backward, even for Turby, they will all have their counterpart in this model, okay, in the continuous version, but they all belong to a different algorithm. And you will see actually quite interesting. They have the same spirit, but the mathematical technique can be very different. Although there is one similarity, which is that it's always, it can be always break down into a local operation, which basically solves iteratively a subproblem, and then continuously build on the whole solution, like what we do in forward-backward. And this model is called Statesbased models, okay? And then again, which I'm not going to talk about, but in the future you may run into are more complex sequential dynamic models, such as factorial HMM, which basically means that not only you have one sequence of hidden states, okay, you may have a whole sequence of hidden states, which all gives you the same observation. Can someone tells me a story behind what could be a factorial HMM? Just to hopefully inspire you to think about some crazy scenarios with complex models.
So say that each hidden state is one street.
I encourage you to not think mathematically. You just go to your intuition and tell, like what I did. When I tell you a HMM, I talk about a casino story. And I say that this model works for modeling a casino. Think about that, because you want to focus on the problem, not the math. Many people learn machine learning and walk away with a whole bunch of equations and mathematics and states and the models and all that, and you forget about it. But if you learn a story, that actually gives you a lot of power down the road. So I ask now, what is a possible story underlying a factorial hidden Markov model? Just graphically, you'll see it now here. In fact, graph is very important, because if I give you the word, it doesn't resonate. But this guy, let's say, it's a dishonest casino. You have a dealer playing trick with you. What about this? Yeah, you went to a casino, and there are 3 dealers. Okay, and each of them basically have their own tricks of playing dice. And then you basically, are the poor guy behind the curtain. You only see the dice roll out. How about that? Right? So that's a story. Okay. So natural story is the most interesting thing that allows you to design interesting models. And likewise, we have something called a switching HMM. Same thing. Okay. So here I will give you a story. What is a state-space model correspond to? Here in HMM, you have an observation of sequence, and you have discrete states. In here, you also have a sequence of observations, such as the signal of an aircraft on the radar. Okay, are these observations, right? And what are the hidden states? Well, the actual physical location of the aircraft in the space. They are not on radar. This is the radar, and this is the airspace. And you can establish, because how engineers are doing, how you calculate your trajectory of your missile is because you see the radar and you do the inference on the true trajectories of the aircraft, right? So that's basically a story. In fact, that's exactly why, our algorithm, to study today was invented, okay, back in the 60s or 50s. And then now give you that, what is a switching state space correspond to? Again, there are now multiple hidden trajectories. Can you just come up with a story? Yeah.
I'm not coming up with a story. I just have a question to this slide. So what is the difference between X and Y?
What is the difference between X and Y?
Yeah, in the middle of the graph.
Yeah, so I see here, X is what you see on the radar. You literally see this. And on radar, there is a coordinate telling you a dot. Okay.
I'm asking about S.
S. Switching. Topmost. S. Oh, okay. Yeah, good. That's a very good point. I can explain to you. But let's have a story again first, right? This S, for example, you can imagine the S are the god. They are choosing basically the two casino players to play. I choose you, you play. Okay, then basically one gets chosen, right? It's the indicator of which particular casino player is going to be in action. So in fact, I would prefer not to explain. You, as the modeler, should now come up with this story. When you have multiple casino players in here, when you have multiple aircrafts in the space, you have one radar screen, how are you going to design your model? Okay, these models, by the way, are not a fact. They are designed by people. It's a choice. Some people designed this model and found it worked. Okay? So you can imagine that this S is just a fact that you don't observe, indicates that which particular aircraft is captured by your radar. Right? The radar are rotating, and whether it captured this aircraft or that captured aircraft, I don't know. Therefore, it's a hidden vector, a hidden indicator. Right? And then the aircraft itself is flying. It has a hidden trajectory. Right? And then, imagine that I have this aircraft, I have that aircraft, and then I have a chain basically selecting, do I do this or do I do that? And then, depending on my choice, I'm going to have an observation of the space of the location on the radar screen. Did you see that? Again, you guys are very puzzled. Get used to this, right? So this is basically the true art of modeling. It's way more important than figuring out the mathematics. Okay, and that's why there exist programs like TensorFlow, like other things, which basically allows you to do no math. Okay, you don't need to do any math, but you need to still design a model. There's no one who does the model designing for you. Okay, and that's also why the so-called AutoML is a fake word, right? You don't automate the design of the model. It cannot be automated because that's reflecting the human knowledge and the human intelligence. You need to tell basically that a radar screen corresponds to an airspace. No automatic mechanism will tell you that. Yeah. Yeah.
Forgive me, I'm sure you went over, but just to make sure I get what different properties does the switching estimate have for the vectorization? Because the stories that we told sounded kind of similar, and looking at the topology, so they look pretty similar. So what?
Yeah, exactly the same topology. Right? So this S, I'm going to again run out of time now, but the S is choosing which aircraft appear on your screen. Clear about that?
Yeah, sure.
Yeah.
The S shows up on both, right? So
What's that?
is it just that we have different modeling assumptions between the two of them, or I can ask offline?
You could have, you don't have to. It's your choice. Again, remember, you are the designer of the models. You imagine your world. Okay. Right? Do you actually assume that there's always one aircraft out of the two captured at this screen. Okay, if you choose to believe in that, you don't need S, right? And if you believe that these two things are alternating appearing on the radar screen, then there should be an indicator to indicate which one ought appear. Then how they change locations and switching back and forth to appear, that's a dynamics we need to model, and therefore need to set placeholders to model it, right? So here, it's very important. I have to spend time on this now. Model design, and also in this, description, you have to be very, very explicit. There is no hand waving. Oh, I saw some observation. There are some inputs, and then there's a black box in the middle. I'm going to get something out of it. No. Okay. For anything that requires to do serious inference, you have to know exactly what story you want to hear, and you have the placeholder of those stories. Okay, the placeholder of the story will be no more, no less than what you want to hear. And then you're going to hear what you want to hear. Okay, many people start a question without even knowing what they actually want to know out of a question. They basically say, oh, I want to get something out of it. Okay, then you will get nothing out of it. Your model won't tell you anything. So here I'm very explicit. You know how many aircrafts you need to put there. You know how to dynamic switch, you put it there, and then they will tell you basically at what time you are going to see which aircraft in what location. Okay, the numbers basically will be inferred from there, but the structure of the facts, okay, and also the listing of all the facts has to be given by you. Okay, so that's basically what is a very, very interesting, that's why it makes modeler not a trivial word. It requires you to be very explicit about your domain, especially when you are in real operation, like running a factory, shooting a missile or something. So again, this is different from ads recommendation. You throw at somebody an advertisement. Oh, okay, you get it. I don't care what Y calls it or whatever. Right. So these are the type of machine learning we are studying, at least in this lecture. So forgive me, I'm going to move on, okay, and I'm going to now do some math, okay. The math is basically not a core, but they are the important tools for you to get those interesting work done. So let me say a few seconds on each slide for some facts about multivariate Gaussian models, because we're going to use it. So we know that a joint Gaussian have this property that you can define subvectors, and the subvector marginal of a bigger Gaussian vector is a Gaussian. Conditioning of a subvector given others is also a Gaussian, and their means and covariance can be computed following an equation. Okay, remember that. We're going to use it. And then there is also a very important technique called the matrix inversion lemma. Again, I don't have time to go over the details. You basically know that there is a way to compute the matrix inversion by somehow putting together the inversion of those submatrices, okay, inside the original big matrix. We're going to use this. Okay, so in fact, there is a tricky way to remember this. I used to remember that. It's a cyclic way of visiting the submatrices, but I don't have time to go over the details today, but you can essentially just copy this equation. The third very important fact about matrix algebra is the following concepts. You know what is a trace of a matrix, right? And trace is a scalar, is a number. Basically, to turn a matrix into a number, you use a trace operation. And then trace has this cyclic permutation property, okay? And also, here are how to do derivatives on trace, okay? And sometimes, you can do very interesting things using trace. For example, we know that the matrix left multiplied by a column and a row, and the right multiplied by a column turns the matrix into a number, right? Therefore, the trace is equal to, in fact, you want to know this. Okay, because it's a number. Okay, and we're going to use these facts a lot on the road to derive basically complex, not complex, but tricky derivatives. And then determinant and of log of the determinant has this following differentiation. Okay, so these are facts. Let's look at a model. What is a factor analysis? Imagine that you have this piece of paper. Okay, and on paper, everything is living in a two-dimensional space, right? You can basically define a center, define a coordinate system, and you can do a point. Okay, and these are basically my points x, okay, which lives in say R2, okay, on the paper. But I now hold this paper either this way or that way, this way and this way. You view it, and you imagine these 2 points on this paper. You can also use a three-dimensional coordinate system to describe that, right? It is so therefore this one is called a subspace or a manifold. Depending on whether you sit on the paper or you sit in this room, you are going to see these points on paper in two-dimensional or three-dimensional space. Okay, and so in this case, we let y to be the points in the three-dimensional space. Okay, and therefore the y and the x must be related in some way, right? You can imagine that how they're related. Well, first of all, the center of this particular coordinate system on the 2 paper, the center, the coordinate of this center in the 3D space must determine basically where are these points correspond to. There's a relatedness. And also how the paper are tilted should also affect how a two-dimensional points on the paper can be given coordinates in a three-dimensional space, right? Therefore, there should be a mu, there should be a pi matrix, a gamma matrix, which actually could relate x to y. In fact, here is how they're related. Y equals to mu plus gamma 1x, or lambda x. This is capital lambda. X is basically the two-dimensional coordinates, okay? And they can be turned into a three-dimensional coordinates by multiplying this matrix. This is a matrix like this, okay? It's called a loading matrix. And then you are adding to the origin of the coordinate system in the two-dimensional system, and then you get y, okay? So this is a graph showing you exactly what happens, okay? Get the point? This is a geometric story. And why this story is interesting, we talk about latent space sometimes. For example, we observed a bag of word or some other continuous observations in our word count space. But you believe that the actual content comes from some latent space, which are lower dimensional. Say there are only 2 topics. Okay, one topic has a certain word frequency, the other topic has other word frequency, and then what you observed is a word vector. Then that basically also leads to this same idea, that you have something living in the lower dimensional space, but your observation is actually in this three-dimensional space. Okay, so this is called factor analysis. Other similar ideas also exist in models like PCA, like locally linear embedding. There are many names. You probably learned some of them already from 701 and other lectures. So today we're going to study how to learn and infer factor analysis models. Okay, so here are the mathematical trick behind it. What is the problem? Okay, so let me repeat the problem. We get some latent factor x in a lower dimensional space that we actually don't know. Even I give it to you, I didn't show you exactly where the coordinate is and how the loading matrix look like. You need to measure it. But what you do know is y Okay, that's basically a point that you can measure its coordinate. And we assume that the x follows a distribution px. And we know that y equals to mu plus lambda x. Therefore, you can also write down p of y given x. Right? Here, let's add a noise. This noise, epsilon, may follow a Gaussian distribution of, say, just a standard noise. Okay? And then our goal is to, the problem is to figure out p of x given y. You observe the data just like you observe in a two-dimensional radar screen. And by the way, the latent space could be lower dimension than the observed space. It could also be higher dimensional. It's just a transformation, basically, from one space to the other. So in the radar case, you observed a two-dimensional points. You want to infer the three-dimensional effects. That's also possible. But the problem is the same. You want to compute p of x given y in this case. Okay, so what I'm going to today is to give you a procedure to make that happen. Okay, it's a procedure you want to remember, which uses nice properties of the Gaussian. So here is a story. We know that the p of x is a Gaussian, right? And the p of y given x is a Gaussian. Therefore, p of x and y is what? Is a Gaussian, right? And therefore, p of x given y is what? Is also a Gaussian, okay? And therefore, you know, we can start from here. How to describe a multivariate Gaussian of two sets of random variables, x and y? Say this is the vector of x and y. How does its Gaussian distribution look like? Gaussian of a mean vector. How the mean vector look like? ux and uy. Right? And how does the covariance look like? Right? Sigma x and sigma y, and then, yeah, covariance sigma x, y, and sigma yx, something like that. Right? And once you have that, we actually know previous pages, if you remember this. Once you have this, you know, this whole thing, then you can write down basically marginal and conditional, just following some standard formula. You plug in the equations out of the terms in here and get it. Right. All right. So that's basically, you know, a key idea for doing inference in Gaussian dispute in factor analysis. Let's compute all these elements, okay, in the matrix. Let's first write down the joint. So we have mu of x. What is mu of x? So because we assume that the x follows a Gaussian distribution of, let's see, do I have a, yeah, I think it's becoming, yeah, normal and identity matrix, I believe, right? So equals to 0. And mu y, how to compute that? Mu y basically equals to expectation of y, right? And then you plug in the, you know, this equation into here. And therefore, mu y basically equals to mu. Okay, very mechanically. And what else? Well, we also have the sigma x. What is that? It's identity. And the covariance of y, this is the definition of that, right? And you just plug in everything, you get a covariance of the y in this form. Maybe let's write something that is not on the page so that I can make sure that you understand. What is the covariance of x and y, just by definition? Just literally, let's copy the definition. The covariance of x and y is defined by expectation x minus mu x, right? And y minus mu y, super. And we can put, of course, a transpose of that, right? And how about let's just expand it. Okay, so x mu x and y equals to what? Equals to mu plus lambda x and plus a noise w, and then minus mu y. Mu y equals to what? Equals to mu, right? So, and then we have expectation of x minus mu x, which is a 0, right? So we should just keep it. And the second part is how much? Lambda x, right? Because this guy and this guy canceled. Of course, plus a noise. Okay. And so this one equals to e of x times lambda x t and plus a 0, right? Because the expectation of this w is 0. Okay, and then do more. Let's take this lambda out. It becomes e of x xt, which equals to what? It is the covariance of x. Identity, right? So, okay, so that's how you literally compute it. Very, very trivial, but you want to remember it. So what I was doing is to basically try use all these local components x and the p of y given x to now write down a full joint Gaussian distribution p of x and y just by filling in all the components in its mean and covariance. Okay, I have now this one, this one, this one, this one, and this one and that one. Everything is there, basically. This one is, so everything is here. Okay, so that's basically copied in here, and now you have this. Okay, clear about that? And then I suppose you know how to help out, right? So if I want to write down p of x given y, what should I do? Well, I basically need to now use these two definitions, right, from the full matrix. And we also know the full matrix, how they look like, right? They basically look like this, right? Okay. So are we done already or not? So up to here, what do you think? We're almost done, right? We know actually everything. We know what is the lambda, and we know the phi, which is the psi, which is the covariance of the noise. And so we just plug in and compute. Are you happy with this equation now? Mathematically, you should be very happy because it's clean, and you have a closed form expression of the conditional mean and the conditional covariance of x given y already. Computationally, you may scratch your head because if you look at this, originally, you only have this phi, which is basically the covariance of the noise coming out of x or coming out of y, which is usually a diagonal matrix. Therefore, inverting or whatever, you don't care, right? It's linear. But now this lambda times lambda transpose, remember, how does that look like? It basically looks like this. I have a lambda matrix. I have another matrix like this. And at the end of the day, I'm going to result in a matrix of this big, right? And if you are in such a problem where, say, you see a huge high-dimensional observation, okay, say image pixels. You want to basically express the entire image into a vector of pixels. Even though, these actually are, you probably heard some words like eigenface in the past, right? How to classify faces or other things. Yeah, a face picture is basically a big vector, okay, of real numbers. But there are maybe 3 groups of faces, maybe women and men and the child, okay, or whatever lower dimensional space. Therefore, if you deal with this equation, then it's basically doing everything in your real observation space. Therefore, this matrix could be thousands of dimensional or even higher, even though that your projection, okay, of the x, in the latent space is a lower dimensional one. Sometimes people plot eigenface just into a 2-dimensional plane that you see, this group of faces there, this group of faces there. They just have 2 different types of 2-dimensional coordinates. Okay. So, need to basically do some other trick where we invoke the so-called the matrix inversion lemma. This is a mathematical trick. So this is basically the matrix inversion lemma. It corresponds to our original, generic definition of the matrix, where I think it's E, F. What's the original sequence look like? Yeah, E, F, G, H, something like that. So let's basically just maybe do something trivial here, just to map each of these into here. So here we have really the E correspond to what? Identity, right? And we have the F correspond to what? The lambda transpose. And we have the G correspond to lambda. And we have the H correspond to psi, right? Okay. And if you look at the term in here, okay, and the right-hand side of this matrix inversion lemma, you see almost one-to-one correspondence. Okay. The only one thing that is missing, that there should be a I matrix here. Okay. Oh no, sorry, I matrix here. To basically make that equation, a one-to-one mapping of this equation. Okay, the I basically is the E here. Therefore, we have a E here. We have a E here as well. Okay. Okay, what I did is basically just to shoehole this part, okay, into the right-hand side of this matrix inversion lemma. Therefore, now your conditional variance can be expressed by this very simple inversion, okay, on the left-hand side of the matrix inversion lemma. Okay, so these two things are equivalent, but they have very different computational implications. Okay, so in here, what is the dimension of the matrix that you need to invert? It's the skinny side of the matrix, right? Basically, you are now talking about having this multiplied by this as this part. Therefore, you are having a lower dimensional matrix, and you invert it. It could be as small as inverting a two-dimensional matrix if you are doing eigenphase projection into a two-dimensional space. Okay, so why this mathematic happens? At the end of the day, your matrix, you knew that it is a low-dimensional matrix, but in here, in this original equation, you go high dimension first, invert it, and then you collapse with another rectangular matrix to make them into low-dimensional. Therefore, you go high and then go low. And that high step is getting you a lot of computational trouble, right? In here, equivalently, you directly do everything into, you go low first, and then you invert. Okay. And likewise, the conditional mean can be computed like this. Okay, so I said mathematics is not as important as the modeling, but sometimes it gives you some practical saving, okay, in this case. Yeah.
I have a math question. So basically, in the equation that you gave for the EFGX, it's a minus sign in the current, but like in V of 1 given 2, it's a plus sign. So I don't think they're in correspondence to each other.
You can play with the, let me leave this as a homework, okay? So there are minus and plus signs here I totally ignored. I think all you care is about the correspondence. You can read the equations and get that point.
But why can't you just ignore the plus sign?
I didn't ignore. I just don't have time to do fact check here. Okay, so the point here is that it's the technique that I want to remember, not the particular way I copy numbers. I may copy numbers wrong. Okay, it is a technique that there are two pieces of main technique. One is to basically do this joint Gaussian mapping, and you should fill in the numbers, not I. I may fill in the number wrong, okay, and you should get it right, but the method is correct. And then once you get this, how can you basically compute conditional mean and conditional covariance? And again, copying the numbers, I may make a mistake, but then I want you to correct me. Okay. Yeah, again, as I told you, it's trivial to basically correct this mistake in here, okay, in front of all these people. I want you to know this technique, okay? Making pieces of Gaussian, conditional Gaussian or marginal Gaussian, blow up into a joint Gaussian, and then use that to do the conditional, and then also to use the Gaussian distribution, the conditional mean and the conditional covariance formula to compute, okay, all these new mean and the covariance based on the building block, and then use the matrix inversion lemma to reduce the dimensionality. These words are the most important thing, okay? Those specific numbers are not important. You can fill in yourself. I'm sure you can do better than me, okay? Because I'm going to reuse technique in the next half an hour to make an even more elaborate derivation that hopefully don't scare you too much. All right, so much for this. There are some nice properties of FA, which I don't have time to go over, but you can read the slides. Let's talk about another geometry interpretation. I hope it's clear already. Let's talk about another problem, learning FA. So what I just did is inference, right? To compute the condition of the hidden continuous states given the observation. And but where do we learn the loading matrix, the manifold center mu, and also the variance of the noise? How do we get that? It is the same as what we did in discrete graph models, right? Learning basically the conditional mean and the and the frequency of every cluster and so forth. So let's first agree on a paradigm that we want to learn. So in which statistical paradigm you think it's reasonable to learn all these numbers? Base is great, yeah. Let's assume that we don't have prior right now. So we could, of course, if you have prior, we can do base. What's the simplest one? Maximum likelihood estimation, right? So that basically is something like star of lambda, star of mu, and the star of psi, and equals to the arc max of likelihood of what? Of your data. What is your data? Y. Okay. Arc max of py, basically. The truth is that thanks to our manipulation of the Gaussian, given x and given x given y given x, we actually could write down in closed form the marginal distribution of py already. Right? We can actually write that, which is in here. Complete likelihood. Incomplete likelihood. So do I have it? Okay, so it is equation. Remember that? We have basically mu y and sigma of y, which actually is expressed in here. Therefore, we can basically write down p of y in closed form. Remember that? Therefore, this is our objective function. Okay, and I introduced some auxiliary matrix. And then you can start estimating all these numbers. How to estimate? You take a derivative of this whole thing with respect to the parameters you want to estimate, lambda or psi or mu. And in fact, you can easily compute the mu already with this. But you kind of see something already a little bit tricky, right? Lambda and psi are together and in the inverse. And therefore, to compute it could be very, very difficult. Yeah, they're non-linearly coupled, right? And remember that our EM algorithm lecture, we ran into the same problem, right? You can write down the joint, the marginal likelihood of the observation by sum out all the hidden random variables, and you have a closed form expression. But when you do derivative of that term with respect to the parameters, you get a lot of things coupled, exponential of sums and sum of exponentials and all that. Therefore, the estimation can be very hairy. Right? Okay, so now I don't want to motivate even more, but let's use the same trick we did in EM. So in EM, what is the objective that we optimize? It's called the complete likelihood, right? We basically are introducing both x and y. We pretend that x is observed. Just like in the EM algorithm, in the mixture of model algorithm, we pretend the labels are known, right? And then we can write down now a complete log likelihood in a way that is hopefully simpler. Okay? So this is how you actually see the whole thing. Okay? It's a little bit simpler than the other one. Just to recap, this is our complete likelihood, and we don't have x, right? And like what we remember what we did in EM is to pretend x is observed, because we can do inference on x given y. And therefore, with this, we can always compute sufficient statistics of X. And all that. And we can plug in so that these variables can be replaced with a constant. Right? Okay, so that's basically what we do. We are going to now use a EM technique, and then we basically could use the inference result. We already know how to write down the conditional mean and the variance of X given Y. Therefore, they are taking this form, and therefore the mean, which is this guy, and the variance can all be written already. Right. And then you use this, to take a derivative of, the psi and the lambda, and you will find that they decouple very nicely. Okay, especially when you get the phi. Phi is decoupled with everything else. And then, you take lambdas likewise. They basically can iterate. Okay, so that's basically our continuous version of the EM algorithm. And the model is known as the factored analysis model. And at the end of the day, basically, you are seeing a counterpart of what we did in the mixture model, in the continuous space, where we have latent variables to be a continuous random variable in some subspace. Okay, any questions at this point? Do we actually know the basic message of what we covered so far? Let's summarize a little bit about this message, right? So the first message is that mixture model and the FA model are different only by what? This is a mixture, and this is FA. The difference is that this one is continuous, and this one is discrete. Right? And then in mixture model, what we do for inference, well, we basically can write down P of X given Y. Right? And we know how to do that. Do you? Basically, it's written down by P of what? X and Y divided by P of Y. And P of Y equals to what? Sum of P of X and Y over all the Y's. Right? And the Y's are discrete, therefore you can literally sum over all the mixture components and compute this margin of Y, and then you get this. And in our FA space, what you did? We have P of X, we have a P of Y given X as generative models. And then the way to get to P of Y given X is what? Help me to recover what I did. Okay, we basically have, X given Y. X given Y, sorry. How to get that? We basically use these two to first get a joint, right? And the joint is a Gaussian. Therefore, we're going to write down the joint mean and the covariance, right? And then we're going to use the property that the conditional of the other half given Y is also a Gaussian. Therefore, we're going to use conditional mean and covariance definition, and also the matrix inversion lemma to compute that. Okay. Therefore, we finish the inference. This is the inference. And then learning. Again, as a review, are there any difference between these two? They both use maximum likelihood estimation. They both have a hidden random variable x as hidden. And they both could benefit from our inference solution. To compute the expectation. Therefore, both can use a EM algorithm to solve the learning problem. Okay, and then the rest are just algebra. You need to basically plug in certain things and do some derivations. Okay, so this is the one-to-one correspondence between this model, and this model. And I really like you to remember some of the basic algebraic techniques so that you can, in the future at least, treat this kind of Gaussian-based models with ease. I have another 20 minutes. I think it should be enough, and derive a very famous algorithm. So about this, okay, the HMM counterpart in a continuous latent. And of course, we have other fancier models. Okay, so this model is called state-space models. Just like in HMM, we can begin by defining the dynamics, okay, as placeholders. These parameters may be not known. We need to actually estimate that. So graphically, they look the same as HMM, but here is dynamics. The hidden states starts from, well, it's, I said x1 here, but x0 here, that we can put 1 here. Okay, the first state is a Gaussian distribution with a zero mean and sigma 0 covariance. And starting to the right, we have a dynamic model as this. The next x is the previous x times a transformation matrix plus some noise, okay, and with a orientational input as well, meaning that the noise may favor a particular way rather than uniform all direction. And then at every state, we observe a observation, which is a transformation of the hidden states to the observation, plus a uniform noise. Of course, this can be more general. If you want to make a nonlinear transformation, you can replace a times x t minus 1 and c times x t minus 1 with f and g functions. Do you recall how we do the same in HMM? In HMM, x1 to x2 is what? It's a discrete transition. We have a transition matrix, right? Starting from one state to the other state have a discrete probability. Here, we don't have that. It's continuous. Therefore, you have to have a linear transformation to manipulate the location. And likewise in here. And again, just to make it concrete, very concrete example. This example is a little bit peculiar. We define the latent space to be a 4-dimensional space. Okay? Imagine just a 2-dimensional motion. Okay? We have a object moving in the 2-dimension space with a position vector x. Okay, position coordinate x1, x2 at time t. And then they move with a velocity, x1 dot and x2 dot. Okay, so these are basically what I call a state, a true state of my environment. Okay, and they are going to follow Newton dynamics to move forward. You can see that this equation is exactly defining the Newton dynamics. The next position, okay, is going to be the previous position times the velocity plus the velocity times the time delta. Okay, so these are no secret. And then its velocity is constant, therefore it's going to be copied. Okay, very simple 2-dimensional motion. And then my observation, okay, is this, which is just it's a very simple, it's a truncation of the first 2 dimension in that 4-dimensional vector space, vector state. Why? Because I only observe the position. I don't observe the velocity. And I also assume a noise. Okay. So that's basically a LDS for 2D tracking. And if you want to write your tracking model, this may be the simplest one. And then the inference problem is the following, right? So suppose that we are given a sequence of positions from 1 to t. Okay, imagine that you look at this screen, and you have a whole collection of coordinates at every time point from 1 to t. Okay, and then you want to estimate the precise location in the real world of that object. Okay, so that's an inference problem. It's called filtering. Given all the positions up to now, okay, I want to estimate the true position of that object at this particular moment. So graphically, here is what the algorithm known as common filter is trying to do. What common filter is trying to do is that it's assuming a sequential, incremental algorithm, which basically starts from just one observation, and then I estimate, a signal, and then if I go to the second position, I'm going to now estimate this, and if I see one more observation, I estimate the next one, and so on. Okay, so this alpha is basically my running estimation of the conditional of the current true state given the entire sequence up to now. Okay, and just like in HMM, people discovered an equation that can establish a incremental procedure, which is that if you know the alpha from the previous time point, okay, and also you know the transition from the previous time point to now, and also you know the observation of today's time point, then you can always estimate the position of the current object at this time point. So this is basically known as the forward algorithm in HMM, right? So spirit-wise, it's the same, but HMM is derived, this is the equation of the forward algorithm. You can see that my current alpha is always a function of the previous alpha times a local function of the transition and a local function of the observation. So my question is that how to derive similar equations in the discrete, in the continuous space, where x, y, all the x's are continuous random variables. So this problem is called filtering problem. Clear about this problem? Are you clear? Okay, great. Thank you. All right. Many people don't even realize that what's the connection between common filter and HMM. In fact, that's the connection. They are the same thing, except that now one is a algorithm, corresponding to the forward algorithm in HMM in the continuous space. And some people confuse the common filter is a model. Common filter is not a model. Okay, common filter is an algorithm exactly corresponding to a forward algorithm. Today we're going to, I have 15 minutes left, we may be able to derive common filter. Okay. Usually if you look at a signal processing book, deriving common filter takes about 2 to 3 chapters. Okay, a lot of complicated mathematics, but let's see how much we can do today. Yeah.
States are continuous, right? So
continuous.
why are algorithms then similar to the forward-backward algorithm in HMM? Because we spend the first function, last function, or backward analysis is different from the forward algorithm, forward-backward algorithm.
You will see very soon why we do why we mention forward backward and why we actually talk about the factor analysis. You will see all that. Okay. Yeah, the connection is very, very non-trivial. That's actually why I want to put all this together so that you can see connection. Remember that the connection between HMM And the mixture model is that you basically put mixed model next to each other. Okay, and then basically you have such a recursive inference algorithm, which actually is making use of the fact that every step is a mixture model. Okay, so in the state space model that we are going to worry about, you have the same story. You are going to basically put the factor analysis next to each other to form this state space model, and then we're also going to have this recursive algorithm to do the inference using our results from the factor analysis. The second inference question is corresponding to the backward algorithm, which I'm not going to talk about. It's called the Rauch-Strobel algorithm. But it is answering the question of not an online inference, it's an offline thing. After you see the whole sequence, do you want to go back and correct your earlier estimation of the trajectory? Okay, what's your intuition? You watch a radar, a radar screen, and you want to, you are forced basically to do a real-time decision that here is my aircraft, at this particular point I need to shoot. Then you have to do the problem one. But if it's an exercise, it's a drill, and after all, you are going to now go back and see the whole sequence. Then I ask you where the aircraft was, at the time particular t. I think it would be foolish to basically still use the online algorithm that gives you only time until at a moment, right? You can always, after certain, more data, you may be able to smooth out the results. So that's basically what's happening in inference algorithm 2, which is a more complex algorithm corresponding to the backward algorithm, in HMM. And here are just results, the experiments. If you look at the 2D tracking problem I just talked about, here the squares are basically, the stars are your observations, the squares are the true trajectories, and the ellipsoids are the filters. You can see that they are okay. Right? And in fact, not bad. You can roughly track, the squares with the ellipsoid. But if you do smoothing, if you look at the whole sequence and go back and correct, you get a better fit. Okay. All right, and our brain arguably is a common filter. Why you can actually on the street, avoid basically hitting by a car or by a bicycler, right? That's because you watch at him and you kind of can predict, in the next second, is he going to hit me or not, right? And where it is, is that person, heading toward, and then you take action. That's pretty much what people are doing. It's what you are running is actually a common filter algorithm. You are basically using sequence of data from 1 to t and estimate the next time step. But you are not doing smoothing at this point. When you do detective work, you actually will do smoothing because the accident happened already. And then you can basically figure out what the car really was. Okay, so much for the story. Let's talk about the common filter thing. Okay. So here, what is the problem? The problem is that, okay, so let's see the data. Okay. You are going to be given the data 1 to t. And your question is about p of x t given y1 to t. Okay, so that's the question. So how can we formulate that? Looks like pretty challenging, right? Do we need to rederive a forward-backward algorithm or something? So now, what if I tell you this? You actually already have this p of xt minus 1 given yt minus 1 to t. You already have this. Okay? And also, of course, you have this p of xt given xt minus 1. You, of course, have that, right? And, of course, you have this, p of yt given xt. You already have all this. Can you get this one? Maybe you can think about the following way. Okay, if I have this already, then I could now start writing down p of xt and xt minus 1 given y of t 1 and t minus 1, right? So basically, from these two, I get this already, right? I'm using maybe a proportional, something like that. And then adding this, can I roughly put p of something like that already? Out of time? Okay, 5 minutes. Okay. And what if I tell you that all these are Gaussian distributions? Okay. Okay, so maybe you can already guess that after all, this distribution, this distribution, and then eventually this distribution are some kind of Gaussian distributions. Okay. Therefore, what we need to do are just a computation of the mean and covariance of this distribution. Okay. Let's define, for example, the mean and covariance to be E of xt given y1 to t, and let's give it a name of mu t t. Okay, and let's also define the covariance of this guy, which is xt minus mu t to be what we call the p of t. Okay, so that's basically our target. We need to compute these two things, which is hopefully already reminding you what happened in factor analysis. In factor analysis, when we say inference, at the end of the day, we want to compute some conditional mean and conditional covariance, right? So likewise in here. So here is a strategy that we can take, and we can cover the details in next lecture. Let's think about this, okay, target from what we know as a prior belief. Okay, suppose that we already know, up to now, this guy, given all this, and a dynamic model moving forward. Can we basically make a simple prediction of the next step without seeing the observation? So this is called a prediction step. You can do that because we know the dynamic system, how they evolve over time already. And then we can compute a new belief by adding this new piece of evidence into that. Okay, and with a combination of the predicted states plus one observation, okay, and update our model, of the p of x given t plus 1 given y1 to t plus 1. This is called the measurement updates. And the key idea I want to say is that here, when you make the prediction p of x t plus 1 given x given y to t. It is a Gaussian distribution. And in here, when you want to put down p of t plus 1, given y t plus 1 and everything else, what you can do is to first write down p of x t plus 1 and y t plus 1 together, given everything else, and then do the same matrix manipulation that we did last time. So today I'm a little bit slower than before, but we should be easily cover that in the next 15 minutes for the next lecture. But the slides are already given, so you can go through some of the algebra there. And the next time, let's see how to manipulate, again, the Gaussian distribution in the scenario of seeing the sequence of observations and then get to the common filter derivations. Okay, so let's continue this lecture on Wednesday.